Easy meeting this morning.
Because
Like
we're six
it.
people.
Also, I'm gonna make a couple of you co-hosts. Hi, Anna. And that is because I'm living in the middle of a construction site these days, and we had several power cuts over the weekend. So there might be a chance that if my neighbors turn on, it's basically the UK model, heat or eat. So if you turn on the heater and the cooking, you have a power cut. That's for each boat independently. So even though I'm not heating or eating at the moment, if my neighbors do it, I'm out. Might be a
Oh,
chance
wow.
if my neighbors turn on, but you're hosts now, so
Sounds good.
that should be fine.
Evening, guys.
Hi.
See, Sarge. How you feel?
So now we got Wado, Spain, Germany, and Netherlands. Anyone else in nice locations? No. You're all here. Well, apparently it's going to get super warm on Wednesday. 21 degrees.
I'm
Here?
excited.
Here. I know. Unheard of.
Wow, the end is near.
So, I'm positive,
It was
Eduardo.
very, very cheerful Monday morning.
That's
Thank you,
just it.
Eduardo.
I mean, 21 degree in the Netherlands by this time of the year.
Here we go. I think that is a full house now, and it is 9:30. So welcome to Neuroccino on this Monday morning. Today, Lilith is going to present on brain repair mechanisms. Lilith, if you can share the link in the chat, please. And then you're ready to take it away. Thank you.
Thank you. Let me share it. You see the screen?
Yes, perfect.
Perfect. So yeah, hello everyone. Great to see you all. I would like to show you this paper. I think it's an exciting topic about cell therapies for stroke. It was published this year in summer in Brain Journal by Ruslan Rast and colleagues. So this paper is a review paper, and it's mainly divided in three parts. The first part is where they talk about what happens with brain after stroke on cellular level. The second part is devoted for different current state of cell therapies that we know what's happening, or if there are clinical trials already, at which stage, and so on and so forth. And the last part is a place where they talk about the mechanism behind those cell therapies, why they work, why they don't work. So I think it's a really nice overview of the mechanism and what's happening in this field. So I would like to start just reminding you what happens on cellular level, because this is what also the authors do. So basically, when we have a stroke, I hope not, but if there is a patient has a stroke, okay, what happens is that blood got occluded in a blood vessel, which means that neurons cannot take the oxygen from the blood. If neurons cannot take the oxygen from the blood, then we cannot create these energy batteries, ATP, molecules that we need to make our brain work in the way it has to work, okay? And for example, one of the things that would stop work are the channels in the brain, in the neuron, and this will lead to accumulation, for example, of calcium inside the neuron. So, and what is calcium? Calcium would also trigger the release of glutamate, which is a neurotransmitter, excitatory neurotransmitter, and that would create too much excitation of neurons around it, and too much excitation is really bad for our neurons and they start to die. So this is one of the way why a neuron can die, excitotoxicity. But that's not, and that happens in the core of the stroke, exactly where the neurons are stopping to get the oxygen. But there is also a region around it called penumbra. Here, there is also not enough oxygen, but it's still enough to keep the cellular integrity, but not electric activity. But this can also turn into a death zone if we don't reperfuse it. And there are actually, I didn't know that, but there is a method FDA approved where you can mechanically retrieve that clot that is stuck in that blood vessel. But you have to do it early, like within 5 hours. And it seems even that method is not really beneficial. So like there are only 6 to 30% patients who can benefit from this. So it's not really 100% like way to go method in this case, okay? But this actually what happens like on neuronal level, but what happens is another thing is we have so-called endothelial cells, which compose the walls of our blood vessels. And they are less sensitive to the lack of oxygen. So they would still start to do something. They would start to release these vascular endothelial growth factors. And we need them, and this will trigger the creation of new blood vessels. It's called angiogenesis, like similar as neurogenesis, but in this case, where neurons are created, but in this case, new blood vessels would be created, okay? Which will promote neurogenesis, and then neurogenesis would promote the angiogenesis. So it's like a cycle, okay? But sometimes what can happen is that there is too much of that growth factor, okay? And we will have too many of those blood vessels, which supposedly should be good, but sometimes it's not because those blood vessels would be immature, okay? So they will be not, and they can, so the blood would start leak into the neuronal like area, which we don't want, okay? In this case, for example, we need those cells like pericytes over here and those tight junction proteins. So we need them to keep blood-brain barrier strong. And if there is too much of that, there will be a leakage of the blood, and that causes like edema, for example, increased intracranial pressure, brain pressure, so all sorts of things that we don't want. But okay, let's say there is not so many growth factors released, and there is no edema. What happens next? So, well, within days to weeks, okay, this lesion just becomes this area, and let's say also penumbra would just become an empty cavity, okay? And what will happen, like that area, astrocytes, a type of glial cells, they would create the scar, which is kind of a bad thing from one side, because that would create a physical barrier for new cells to grow. But at the same time, they are like they are not villains of the story, because astrocytes, we need them to protect the healthy tissue, because in that stroke area we have a lot of inflammatory toxins, and we don't want them into the healthy tissue. So that's why they create this, but at the same time, new neurons cannot grow back in that area, in the core or like penumbra, for example. Yeah, so this is what happens. The scar is created, and then potentially long term there might be also accumulation of neurotoxic proteins in distant brain regions that are anatomically connected, so they were not initially affected by the oxygen, and they would also start to degenerate, like as a secondary process. Then the authors start to talk about the endogenous stroke recovery mechanism. I think this is really interesting that in that moment we would have some, like adult brain has its own stem cells, for example, neuronal stem cells or neural progenitor cells, not stem, just progenitor cells. So they are located in like two places. One of them is the dentate gyrus of the hippocampus, and the other one is subventricle zone. Okay, and when this stroke happens, it's so cool that those cells are programmed to travel towards that lesion site. And researchers don't know yet the pattern, the distance, the route, and the efficiency of that migration. Because what happens that sometimes, and as I understand, they would die while traveling to that region. So this is, I mean, a bit strange. If cells are programmed to go there, why would they, in the end, most of them die? So, and here comes the idea of the cell therapy. So maybe we can somehow promote this process that would trigger endogenous brain mechanism, internal brain mechanism to repair itself, or just put new cells that will become that would become the neurons that we need at that moment. So that's the idea behind the cell therapies, and it seems that not preclinical but already clinical testing, so not on animals but on human, they're already, as 2 decades they started this. And there are many companies or many research groups that are doing that. And for example, Starting 2 or Masters 2 or Treasure, they are all around phase 2 or even phase 3 of the clinical trials. But unfortunately, the picture seems not as good as we would have liked to, because, for example, like Starting 2, it enrolled like 60 stroke patients. The other one is 77, the other one is 300, and all of them show that there is no significant difference between the control group and the experimental group. Some of them hasn't finished yet the trials, or some of them say that, okay, there is some effect, but they don't do any correction for multiple comparisons. So some of them just even like prematurely they were terminated. So yeah, apparently there is some problem at large scale. They're not finding the effect. So this is interesting. And one of the reasons, and the authors talk about later, is that the problem is the high mortality of the cells that are transplanted to that hostile for the stem cells environment. So maybe for some, I don't know, maybe for some patients, the cells can stay stronger and promote the brain repair, while for other patients, it would die faster. So one of the ideas now researchers are directed to find ways to kind of toughen up the stem cells from the lab, so they wouldn't die that fast when they are transplanted into the brain. Yeah, and then the authors talk about, and that's the last part, about that potential 2 mechanisms behind those cell therapies. One of them is direct, another one is indirect. The direct one is when so the direct cell replacement allows grafted cells to differentiate. Grafted cells is transplanted cells to differentiate into mature neurons or glia. So, and then integrated with the host brain networks. But basically just we need this type of neurons and in this area, and you would regenerate a new type of cell there. And the second type, second mechanism, second way is maybe when you transplant a stem cell or even like through blood injections, they would promote endogenous mechanisms. So it's not that they themselves would become a neuron, but they would release some, let's say, growth factors that would promote, I don't know, angiogenesis, and that one will promote neurogenesis by own mechanism of the brain. Okay, and so for example, one of the examples for the indirect one is that if you, for example, use some, as I understand, like if you inject primary human umbilical cord blood, which contains a lot of stem cells, so you are not actually putting the stem cells in the lesion site. So if you use them, then they would communicate with some peripheral organs. They will migrate there, like lungs, spleen, or other lymphoid tissues. And from there, they would interact with the immune cells and generate anti-inflammatory environment that will promote the stroke recovery. So it's very indirect way that would trigger the mechanisms of the brain that to fix itself, which is, I think, is very cool. Yeah, let's see the time. Yeah, another thing that I want to say is about this picture is, for example, all the trials, clinical trials that we have at the moment, most of them are using mesenchymal stem cells. But recently they created another type, like not created, like managed to produce this type of cells. It's induced pluripotent stem cells. And these cells are, they can differentiate almost in anything that we want. So for example, if we have neural stem cells, they would differentiate into neurons or like glial cells, while they would not be able to differentiate into pericyte-like cells. And we need them to contain the blood-brain barrier strong. So we would not have this, because angiogenesis promotes neurogenesis, and this is important cycle. That's why these ones, okay, they can also differentiate into pericyte-like cells. The cool thing is that there is not yet the clinical trials in a stroke patients, but these cells already shown some efficiency in treating Parkinson's disease and age-related macular degeneration. So for now, there is no use of that type of cells in clinical trials, but hopefully they are more, they are stronger and they have more put capacity to differentiate in anything we want. So maybe it will work for stroke. I don't know. What else I can tell about this paper? About the scar, maybe also interesting part is that so the thing is, I said that these astrocytes, they create this physical barrier, and then you would think, okay, what if we just transplant it earlier on when there is no scar yet? transplant a stem cell, and what will happen that our brain has certain type of environment, chemicals and factors that produce at a certain moment, and at that moment our brain needs to create that barrier. So if you put a stem cell, that stem cell will eventually differentiate into astrocyte and create that physical barrier. So there is a certain stage that our brain has to pass and to protect the other part of the brain. But this astrocyte scar also helps for putting those stem cells. It creates like a physical barrier also to help to in this process of cell therapy. I think this is really a very promising field. Also, there are some new advances in technologies where they can look how the transplanted stem cells communicate on molecular level with the stroked brain tissue, to see what happens, why some of them are dying. I think with this will be possible to see better what's happening there and not just hoping for that things will work out by themselves. And the last part where the authors just talk about some future challenges or current challenges, and there are lots of problems also in the way it's structured. The clinical trials, for example, not all of them report, not the outcome about the mortality of cells is not reported most of the times. So this is a problem, and yeah, there was a meeting where they created new guidelines on how they can improve the process and transparency of the results. Yeah, and the last thing, this was totally like, I don't know, sci-fi stuff. There might be also some navigating micro robots. They didn't expand it so much about it, but I think it's cool. Maybe this is, you put stem cells in those, I don't know what are those, but navigating micro robots that would travel towards a lesion site and they will not die. So I don't know. I think this is a very interesting and promising field. Really looking forward to see what we will have, I don't know, in 10 years about this. Yeah, that's it. Thank you.
Lovely. Thank you, Lilith.
There are 30 messages or
Based on our chat in the background, I guess there is many questions and comments. And the first one who has her hand up is Eva. Take it away.
Hey, thank you for the presentation. Yeah, it was really interesting. I was wondering, so if I understand correctly, in this space there is nothing anymore. It's a hole. So in regrowth or just growing hearts, for instance, I know that if there is a matrix, the cells know where they are and then they know how they need to grow to differentiate. But then in this space, how do they know how to differentiate? How do they know? Yeah. Is there anything that is going to give the cells the information to grow properly, even if they were successful in doing so?
I'm not sure if Ray actually described exactly how they know that this is the moment where you have to differentiate into something, but I think it's about the brain chemicals that are around that area that would start to because those things that would not exactly in the middle of that hole will start to create the neurons, but around that lesion, so in perilesional areas. I don't know if it's possible just, regrow back the whole matrix of the brain. I don't know. But there are some methods also now where they can use brain organoids to kind of protect those stem cells from dying. So, more like a bubble that would help them to not die prematurely. Yeah, but this is all I know. All I
And
understood.
here the neurotoxic chemicals have already been washed out by the time they would do this transplant.
It depends because they are also trying at the different time points to do that, as I understand, like because earlier on, if you do it, there might be problem with the astrocytes, and but if you do it too much later, maybe it will not work as much as you would like. So it's also really time dependent, the cell therapy. And I think in here maybe they tell the time. Yeah, for example, in some cases they put it in subacute, acute, and subacute, and sometimes chronic. It's all, and also I might be also the understanding of acute, subacute, and chronic would differ from research to research. So,
Okay, thank you.
you're welcome.
Thank you very much. So there's a couple of things in that paper that puzzled me about the treatments and the timings, because as far as I'm aware, there's 2 FDA-approved methods, and they go beyond the 6-hour window even. But
They are what? There are other FDA that you can do
yeah, so you
after
have
6 hours.
thrombectomy and thrombolysis, and they both, but it's different mechanisms, but they're both used to treat acute stroke.
Well, they
Beyond
say beyond. Okay.
beyond.
Well,
So
it says here.
I know when we started, it was a 3-hour window, and then even back in 2010, it was extended to 6 hours, and I think now it's even longer than that. But it might depend on the country, on the guidelines where you work. Because a lot of strokes are wake-up strokes, right? So people come to the clinic and they don't actually know what the exact onset was. Anyways, so there is a question from Mish, and then we take the question from YouTube, which I think would be a nice add-on to that. Mish.
Thank you for this great presentation. I had a question because it's like putting some stem cell is really in order like to recreate the soma of the neurons and through the specialization that will occur in the area. But like the lesion often extend to the white matter, and sometimes is only in the white matter where you just have an axon. And how does the stem cells gonna figure out an axon or grow like 10 centimeters connection in the brain to fix the communication? I just wonder, and that made me really curious. Do they speak about that, or is it like very we go fix the
Yeah,
cortex
I think you can also do like sort of preconditioning of the stem cells. So induce that, make it, for example, you can make these induced pluripotent stem cells pretreated in a way that it will become, for example, an astrocyte-like, or so maybe there is a way where you can precondition them and then make them grow in a certain way because they already started the process, the chemical environment make them to start the process of creation a certain type of cell. And they also talk about, I want to see if yeah, for example, here they talk the glial enriched cells are likely more suitable for white matter strokes, whereas neuronal progenitor cells have been preferentially tested in cortical strokes. So there is also some, depending on what you want to regrow, you would choose different type of cell. And even if it is, let's say, this superhero stem cell that can differentiate in anything else, you can precondition in them in a way to be a certain type of cell. So
But then if you add the factor of time, any gray matter lesion will have an impact on the white matter, and any white matter lesion will have an impact on the gray matter. So then you need two different stem cells to fix.
I guess where the core starts, if it's in the beginning is more like white matter stroke, white matter damage, then you would start with it, so it will not go on the secondary effects. And if it is just primarily like the core, the surface, I don't know, it would rather you start with more, for example, as it says here, neuronal progenitor cells for the cortical strokes that affect gray matter. Did I answer the question?
Yeah, it's still not entirely clear to me how that would then work in practice, but you answered the question, given the
I think it's really also I had a feeling, I mean, there is a lot of information here. Authors even like, I've never seen this. They apologize for the that they didn't include all the citations. There's a lot of data about it, research about it, but still like exactly the mechanism, how with what interact and when, at which moment is still really unclear. But the new methods like this one might help to understand the communication between the host and the grafted cells to see what's happening. And exactly
when you talk about pre-programming the cells, so obviously when axons grow during development, there is guiding factors and also stopping information. How do you pre-program that? How do you make sure that the connection grows to where it's supposed to grow?
Not sure if it's the lack of my knowledge or the paper doesn't talk about it. But there is this thing. Yeah, like see, they talk just preconditioning, pretreatment. Oops. Yeah, I don't know if they talk exactly the mechanism of how this happens. Yeah. And in details, like how do you do the preconditioning of the stem cells? They talk mainly about what happens in the brain when you transplant it, but they are not talking about the process of how to kind of pre-program them towards becoming like astrocyte type or another type. I think it's another whole it's a methodological issue, while here they talk more about the mechanisms in the brain after the transplantation.
Right, because that's one of the questions that came up in our chat while you were presenting is like, naturally, when you have a stroke, you would end up with a cavity, right? There's no regrowth in the tumor, in the stroke lesioned area. But if you can actually then use stem cells to trigger regrowth, and you reconnect in the end, the quality of the connection is a different one. So you may be able to reconnect, but you may not be the same person afterwards. Which I thought was an interesting point that came up in the discussion.
Yeah, I don't know if it will be different person or not, but I don't know. It doesn't say here exactly in which logic they would grow back, or if it's going to be the same or not the same. But I feel like if there is a system that would like provokes to create certain type of connection, it will do it in a way that the system requires. So I think the environment of the brain will create something, but I'm not sure if it's less likely that it will be exactly the same. But the whole idea that we can affect it indirectly to boost somehow those stem cells to regrow both the blood vessels and neurons, I think this is very interesting and so strange that we can repair ourselves in the brain. We just need a little bit of boost. So
But connected to
that
that, I'm just going to quickly throw in the last question from YouTube, which is, can we reconnect a severed axon to a different neuron in vitro? And people in the audience are welcome to chip in. Any
yeah,
thought?
not sure.
Mish, Chris, any thoughts from your side?
So there is this work that emerged from originally the study of frog and like genetical making of frogs that can regrow anything. And that's how they started like creating new drugs that they inject in the brain. They inhibit the gene in humans that prevent the regrowing of fibers. If I remember well, there is this paper in Brain on the nuclein 3, and if I remember well, because I'm not a genetician, it's an inhibition of the P52, and this led to the regrowing of fibers. So if you crush the spinal cord in mice and you inject that drug, the spinal cord reconnect, even if it was crushed, which is the worst injury it can have. And it worked also for the optical tract, and mice can see and walk again. There was a paper in Brain 2015, something like
Does
that.
it reconnect from the same neurons to there?
Exactly. Yeah. Like the fiber
But in the
regrow and
case of
reconnect.
stroke, you lose the neuron itself, no?
It's only about the connection there. It's not about if the neuron's gone, neuron's gone. It's not.
Yeah,
gonna
but
solve
if
that.
you still have the neuron, the axon, and you regrow a new neuron with a stem cell, could you make it reconnect with an old axon?
Well, the axon will be
Theoretically.
the
But
axon will
you
be
don't even
gone.
have to regrow the neuron, right? You can just have two neurons, one dies off. Can you just take the Y and plug it into the other neuron, basically?
Well, but the other neuron isn't, because there is one axon. So can you like the other neuron will already have an axon, no?
Right. The
Mm.
axon is dying
Sure.
so fast
Yeah.
after the soma is gone. It's just, it's not possible to use it.
Yeah.
And that's unfortunate, but that's just the way it is. If you guys are interested, there is some good science fiction on the subject matter. From what was his name? Oh damn! I'll put like as a comment to the video. I'll find the reference. It's a novel. The same guys that did like a novel that inspired the movie The Arrival is doing this novel about like scientists that discover these fantastic drugs that can repair the brain, and how injecting it into the brain of people like makes them smarter, and then like everybody gets like completely nuts on that drug. It's very
Is that the movie we watched a while ago?
No, it's different.
Different. Okay.
It's actually more scientifically accurate.
Right.
Absolutely.
Well, our time's up. Put it in the comments of the video.
I'll put it in the comments. I
and everyone
promise.
can watch it. Thanks for joining us today. Thanks for presenting, Lilith. And I look forward to next Monday morning. Have an exciting week in science. Bye.
Bye.